We're going to talk about the average rate of change. We can find the average rate of change by finding the slope between 2 points. So if we look at this equation, m equals f of x2 minus f of x1 over x2 minus x1. This is the equation for the slope, right? M equals slope. And this is the same thing as pretty much just saying the change in y over the change in x. And in particular, if I take 2 points and I find the slope between those 2 points, that's going to give me the slope of the secant line. So remember, secant lines pass through 2 points on a graph. And when I find the slope of the secant line, that is also the same thing as the average velocity. How do we find the slope at exactly 1 point? So with average velocity, you use 2 points and you find the slope between them. But what if we wanted to find the slope at a particular point, at a particular instance? So we get some estimates of the slope as we get closer and closer to some point x1. So as we're getting closer and closer to a point, that sounds just like limits. Okay, we just finished up the limits chapter, and we're going to be using that idea again. So here we have the same equation as we had in the previous slide. The difference here is that we do have this limit in front, right? The limit as x2 approaches x1 of this function. So this is saying, again, the change in y over change in x, but x2 is approaching x1, so it's getting closer and closer and closer. So with the limit in front, this slope is actually the slope of the tangent line. So the tangent to a curve is touching at 1 point. So this is the line, so the slope for the line that's at that 1 point. And it's also called, I'll put this over here, instantaneous velocity. Okay, so when we have the slope of the secant lines, we have average velocity. And then when we have the slope of the tangent line, we have instantaneous velocity. So the velocity at a particular instant. So secant lines, as they get closer and closer together, the points, they become the tangent line. So they start getting slopes that are similar. So as we get closer and closer to a desired point, we can write the limit of the slopes of the secant line as this. And again, notice that this is very similar to the previous slide. So I'm just going to show this again. So instead of using x2 and x1, here they're using x and a. It's the same idea. It's just written different ways. So we just want to make sure that we're used to seeing these different types of equations because they're all really the same thing. They're just written a little bit differently. So again, I'm just going to write here, this is basically the change in y over change in x, but it's the limit of that. Okay, so once we take the limit of the secant lines, we have the slope of the tangent line, which is the slope at exactly 1 point. So if we look at this, I guess a little confusing graph, if we look at the blue curve, so the blue curve is our function, and we have a secant line, which is this black line, and we have a tangent line, which is this red line. So the secant line, we can see these 2 black dots, and the line connecting them is the secant line. So right now, the slope of the secant line is not the slope of the tangent line, right? The secant line maybe looks like the slope is, I don't know, 2 or 1 or something like that. And the slope of the tangent line looks like it's maybe like a half or, some type of fraction. But as we get closer and closer on that secant line, so if we see the black dots, I'm going to, I'll use green. So if I pick a point, see this Q point here. So if I move Q, let's say I pick Q to be this point, right, a little bit farther down, and I'm still using the C point on the bottom here. If I draw the tangent line, or sorry, the secant line between these, okay, notice the green line is a little bit closer to the tangent line. Like it moved from the black line and now it's getting a little bit closer to the tangent line. If I do this again, let's see if I do it in yellow, I don't know if you'll see. Okay, so if I put a yellow dot here a little bit closer, again to the C point, and I draw the line through them, right, the yellow line is now getting even closer to the tangent line. I'll do one more. What color? I guess I'll do black again. So let's go pretty close here to here. Right? It's getting even closer. So if it gets even closer and it's like super, super, super close together, those 2 dots, it's going to end up equaling the same slope as that tangent line. So this is all helping us figure out what a derivative is. So what a derivative is, graphically, it is the slope of the tangent line, which is the limit of the secant line. Numerically, it's a number that represents the instantaneous rate of change of a function. So in context, it has units. And then algebraically, it's this f prime of a, and the little apostrophe, you say prime, so f prime of a, which is the derivative, is equal to the limit as h approaches 0 of f of a plus h minus f of a over h. So this should look familiar to you from pre-calc and possibly algebra 2. We are going to talk more about this particular equation in the next lesson, but for now, just recognize what it is, and we're going to work with it a little bit later on. So why do we care about slope so much? So great, we find slopes of points and all that stuff, and great, but what does that help us with? So what does the slope represent for a position graph? So here we have a position versus time graph. Okay, so if I wanted to find the slope of the different pieces to this graph, that is actually going to be the velocity. So what does the slope represent of a position graph? The velocity. Okay, so remember, slope is like change in y over change in x. So the y-axis is our position. So I'm just going to write POS for position. And the x-axis is our time. So we're doing position over time. And in terms of the units, the position is in meters in this case, and the time is in seconds. So the velocity would have units of meters per second because it's the slope of this position graph. Now again, how is that useful and how do we use that information? Well, I'm glad you asked. So here we have again the same graph of position versus time. By looking at this, we can interpret things about the velocity. So we want to know, when is the velocity positive? So remember, velocity is really just the slope of the position. So when it asks, when you're looking at a position graph, if it asks you about the velocity, it's really asking you about the slope. So when is and I'm just going to write slope here instead of velocity. So when is the slope positive? So we want to know when the velocity is positive, we're looking for the slope. So when we look at this, I'm just going to kind of color it in here. So positive slope would be here's positive, and then we also have a positive slope here. So it is positive on the intervals from 0 to 10, and then also again from 40 to 55. When is the velocity negative? So again, that's asking me, when is the slope of my graph negative? So we can see the slope is negative here. So that's going to be the interval from 15 to 40. And then lastly, when is the velocity 0? So again, they're just really asking me, when is the slope of my graph 0? So we can see that the slope is 0 right here, and that is the interval from 10 to 15. So again, just kind of like a recap of what we talked about. The average velocity, that is really the slope of the secant line. So I'm just going to put slope of secant. And the way that you can think about this is just displacement over time. So it's just the change in y over change in x between points. The instantaneous velocity, remember that that is the slope of the tangent line, and that is the limit of the secant line, which is the limit of the change in y over change in x. And sometimes you might see, I'm just going to write this here, this is the same thing as saying f of x minus f of a over x minus a. And this one is the same thing as saying the limit as h approaches 0 of f of, x, let me erase that, minus f of a over x minus a. Okay, so don't get caught up with all the different equations right now. They all mean the same thing. When we get into the next lesson with this, hopefully it will make more sense, but for right now, just being able to identify them is helpful.